this video we're going to talk about light. Now light is a phenomenon that we're very familiar with, we see it with our eyes. But we have come a very long way and now we have some understanding of what light actually is. And we believe that light is in fact a transverse wave, a disturbance in the electric and magnetic fields of space that gives light some unique properties. Light travels at 300 million meters per second through a vacuum. It travels slower than this when it goes into different materials, but it never travels faster than this, always 300 million and no faster. Now, what is going on is that all of space is full of electric and magnetic fields, and these are present. You can see the aurora interacting with Earth's magnetic fields, even though they stretch out into space. And even though there's no particles out there, there is still a magnetic field. It's a different kind of thing. Now, because the electric and magnetic field extend through all of space, that means that a disturbance in those fields can propagate from one side of the universe to the other in the form of light. And light is obviously what comes out of the sun and comes down and brings energy to the Earth. Now, if we were to try to draw light and represent light on this board, there are two types of diagram that you need to be aware of and what they both mean. Now, first I want to talk about a ray diagram. A ray diagram follows the direction of propagation. So if I had a candle here, candle, and I had an observer here, and I represent the observer with an eye that is looking, then what I could draw is a straight line, and I always draw it with a ruler from the candle to the observer. And there's nothing to be afraid of here, but there is something conceptually quite challenging. One of the things is that there is not just one ray coming out of this candle. This candle is in fact giving off rays of light in every direction. But what we're choosing to do here is concentrate only on one of them. We're ignoring all of the rest. We're only interested in the ray of light that is entering our eyeball. Now, the path of a ray of light in space is always straight, unless space itself is curved. This means that light will go the shortest distance between two places. Light can be seen to travel in straight lines. If you observe a shaft of light coming in a darkened space, you can see that it travels in the most straightforward path. The second type of diagram that I want to draw is a wave-front diagram. So a wave-front diagram is a way of displaying it differently. Wave-front diagram, because now what I want you to imagine is along the direction of this ray of light, what is actually happening is this transverse wave is oscillating like this. And if I was to look at this, I would actually see that, like an oceanic wave, that it actually moves along, and it is that movement that causes it to propagate through space from here to here. That peak, though it is oscillating up and down, a second later that point that is at peak would be to the right, and then a second later to the right a bit more. And so even though the actual medium is only oscillating up and down, what we see is the apparent position of the peak moves and translates forward like a wave coming into the shore. That's what it would look like if we could actually see it on this sort of scale. Now, of course, what that means is that I have a wave peak here, and I have a wave peak here, and here, and here. And if I was to track the position of these peaks, sometimes called crests, then I would find that all of them would be travelling from the candle to the eye. And sometimes it is useful to depict light using a wave-front diagram. So what is basically happening is now we ignore all of the rest of the wave, the trough, and all of the rest of it, and we could basically draw wavefronts moving along. And I should do this with a ruler, but there's no reason why. And you can see that the wavefronts always move at right angles to the direction of the ray, or they're drawn at right angles to the direction of the ray. So now hopefully you can visualize that what we mean by a ray is a single one of these waves as tracked by the wavefronts as they move in that direction. Now, as we explore light, we're going to use these two diagrams to help understand and make sense of the phenomena that we are seeing. Now, with this equipment, we can investigate some of the properties of light. And what this is a laser that is going across this board here. And I have a protractor, and I have a small segment of mirror. Now it looks like a piece of metal, but believe me, this is reflective. And what it's going to do is it is going to reflect the laser light back in the direction that it has come. Now, one of the very first things that we want to do with light is understand this phenomenon of reflection. Now, you need to understand that it's not just light that reflects. If you've ever kicked a ball against a wall, you will find that the ball reflects back against you, called a bounce. But with light, it is a marvellous thing. When light is reflected, it goes through some changes, but not everything changes. The frequency and the wavelength of the light remains unchanged because the light does not speed up or slow down as it reflects. It just changes direction. I'll put a piece of paper in here. Hopefully that will make it a little bit clearer. And what I'm going to do is I'm going to put my mirror on the paper. But before I do that, I'm going to draw a line to represent where my mirror is going to be drawn. So I can draw it anywhere I like. And so this is my mirror. And what I do to represent a mirror on a diagram is I put some little lines on it like this to show that this is inside the mirror and that the reflective surface of the mirror is on the right hand side like that. Now, of course, what I would then do is I would place my mirror segment on it just here, and I would keep it lined up. Now, what you can see is happening at the moment is that the light is hitting the mirror and is bouncing straight back towards the laser. Now, one of the things that I want to look at is what happens when the laser light does not hit in a straight line. So the first thing I'm going to do is, now that it's lined up like this, I'm going to put two little X's here and here. And you see what I can do is I can take the mirror away and I can draw a line here which represents the line that is at 90 degrees to the mirror. And this is called my normal line. It is the path of light going straight in and bouncing straight back out again, 90 degrees to the surface of the mirror. And what I can do is I can change the angle at which the light is entering the mirror. And I'm going to do that placing a protractor on my mirror line so that 90 degrees aligns with the normal. Now what I can do is I can cause the rotation to occur. And I still want the ray of light to hit the mirror just there, and you can see the reflected ray of light is now coming across over here. This would be clearer if I turn the lights off, and so part of this experiment you'll have to do under low light conditions. So I turn the light off. Now the laser line hopefully should be clearer, and what I'm going to do is I'm going to investigate what happens when it goes in at 90 degrees. So I'm going to put my two little lines on here and here, and sometimes it helps just to tip the mirror just slightly so that it's clearer where the reflection is occurring. And I'm going to mark that off as well. Now if I was to then remove that apparatus and with my ruler join the dots, course, it's quite hard to join the dots by laser light, but we're going to give it a go. And so this here is the reflected wave, and this here is the incident ray. Now I'll turn the light back on so that you can see what I've drawn. What I've drawn is this. A ray of light went in, and I draw an arrow to show the way it was going, hits the mirror, reflects off the mirror, and bounces back. This one going in is known as the angle of incidence. This one coming out is the angle of reflection. Now what I mean by that is that the angle relative to the normal is the angle of reflection, and the angle relative to the normal is the angle of incidence. Because of course this is the incident ray going in, and this is the reflected ray coming out. So what? I've shone a laser beam of light at my mirror, and it's reflected back again. And this is all within our common everyday experience. So what's significant about this? And it's this, that there's a mathematical connection here between it going in and it coming out. If I return my protractor to my diagram, I see that the angle of incidence here was 10 degrees. The difference between 90 and 80 is 10 degrees. And the angle of reflection here was 10 degrees. It reflected out at the same angle that it originally went in relative to the normal. So the incident ray had an angle of incidence of 10 degrees, the reflected ray has an angle of reflection of 10 degrees. What I find is that no matter what angle I shine this in at, what I find is that it always comes out the same angle. And this is called the law of reflection. So here we have the mirror, and we're going to draw well, best I can, the normal line. Remember that the normal line is at 90 degrees to the surface of the mirror, and it is against this normal line that we measure our angles. It doesn't matter if it's coming in to the top or if it's coming in from the bottom, does not matter. So we draw now our ray diagram of this situation. Now what I can do is I can get my protractor, and just to make this diagram accurate, I'm even going to use my protractor on the board here. And it's quite small, the protractor is, but if I'm going to send it in at 45 degrees, I want it coming out at 45 degrees. And so this is how I would draw. So we're going to have the ray coming in at the bottom. Here it comes, the incident ray. And that ray of light hits the mirror and bounces out once more. Notice I always draw these with a ruler. I always put the arrows on. This is the reflected ray. Now notice before the incident ray went in at 10 degrees to the normal, so that the angle of incidence would be 10 degrees. And then it was reflected out at 10 degrees, the other side of the normal. Here, we're at a much larger angle. The angle of incidence here is 45 degrees, and the angle of reflection is also 45 degrees, much larger. But you can see that this law of reflection is always true. It means that the light reflects out at the same angle at which it went in originally. This is called the law of reflection. And that this angle here, sometimes given the symbol I, lowercase, and this given the symbol R, lowercase, is that the angle of incidence I is equal to the angle of reflection R. If it's it's 10 degrees going in, it's 10 degrees coming out. If it's 45 degrees going in, it's 45 degrees coming out. But I want you to take this one step further. I want you to compare this to your understanding of looking in mirrors. That you only see yourself when you stare down the normal line. There you are looking back. But if I look at a mirror at 45 degrees, I no longer see myself. I see a reflection of what is over there. And so it matches our everyday experience. So there's nothing challenging here. This is the world as we've always known it. So here I am in the boys' toilet. And I want to prove to you something with the mirror. You see, the mirror, as we're familiar with it, creates something known as a virtual image. That there is me here in the real world, and then there's a version of me that we see in there, in the reflected world, in the virtual world. But that is simply an image. It doesn't really exist. It is just the light being returned to me. And there are some key characteristics to the image of me. First of all, this image is as far behind the mirror as I am in front of it. So if I take a ruler, I can see that I am 1 metre away from the mirror, but that the mirror is 1 metre in front of my image. So my image always forms at the same distance behind the mirror as I am in front of it. Now, there are 2 more things about my mirror image. The first is that it is upright. I am the same way up in this mirror as I am in real life. I am not inverted. And secondly, I am laterally inverted, which means that the right-hand side of me in the real world is not the right-hand side of my image. For example, if I stand here and I hold up my right hand, you can see that my image is holding up its left hand, and that it is a mirror image of what we have here in the real world. When light reflects from a surface, one of 2 things might happen. Those light rays may reflect in a regular way. That each light ray could, as demonstrated by this laser, hit the table and then bounce to you. It's the reason why you can see the green laser light on the table. But what might happen is the roughness of the table might scatter those reflected rays of light, so that the image that would normally form, say for example if you looked in a mirror, would be completely disrupted. Now, it is by this mechanism that we see everyday objects, the table, the carpet, and most of the items in this room. Light is reflecting off these surfaces in a diffuse way. This means that each ray of light that is coming in an orderly fashion from the light source is scattering in all different directions, some of which are coming to you. It means you see the surface of the object, but you don't see an image forming that is the reflection of the light source. Whereas here we have an entirely different situation. The light source of the sun behind us over there is striking the top of this skylight. Each ray of light is coming in a very orderly fashion, with all of those rays of light being parallel to each other. But the very smooth surface of this skylight is allowing each one of those rays of light to obey the law of reflection, so that the angle of incidence equals the angle of reflection. And if it comes in at 30 degrees relative to the normal, it would be reflected at 30 degrees to the normal. Meaning that all of those parallel rays of light reflect off the surface and come back towards you, being almost indistinguishable from the original light source. What is forming in this surface is an image, a virtual image, as if this is a mirror. Now, any flat enough surface is going to give rise to a reflection like this, be it a glass surface, a very shiny metal surface, or even the flat surface of a puddle. All of these can have a specular reflection. A specular reflection is when the light rays continue in an orderly fashion and a virtual image forms. If you look at sunlight in a puddle, that is a specular reflection. Actually looking in a mirror, that is a specular reflection. So here on the left we have a surface that is so smooth that it is going to give off a specular reflection. If I was to draw some rays of light like this, and these are coming in, here they come, then what happens when they hit that surface? Well, they follow the law of reflection, and they all get reflected at the same angle at which they went in at. So you can see here that what happens is that each one of these gets reflected at the same angle relative to the normal. And so if you were here and you were to witness these rays of light coming towards you, it would look exactly the same as if you were here and looking at the original incident rays. And so whatever image you are looking at, you can see now reflected in the mirror. Now for this to occur, the surface has to be very, very smooth. Just how smooth? Well, the imperfections in this surface have to be of the same scale or smaller than the wavelengths of light. And that is, the wavelengths of light are of the order of about 5 times 10 to the -7 meters, which means it is about 0.1 of a micrometer. Anything smaller than that would, to the light falling upon it, be considered an entirely smooth surface. Anything larger than that, and it would start to create this situation here: a wooden table, a carpet, a plastered wall, skin, clothing, all of these things that give off a diffuse reflection. So what I have coming in is I have the same rays of light coming in now, like I did before, but the outcome is somewhat different. So here's the rays of light. What happens is that each one of these still obeys the law of reflection. There's nothing unusual going on here. It's just that if you now consider that the surface, and I can do this with a different colour just to demonstrate the point, the surface now is like this, which means the normal is like this, which means for that particular ray of light, its reflection, obeying the law of reflection, is going to be this way. The next one, well, that is the direction of the surface, and the normal, so that one too is going to end up reflected over here somewhere, probably even more acutely than the one before. Now on the third one, what you can see is that the normal here will be this way, which means that this one would end up being reflected right over here. Totally scattered, two going one way, one going the other. And that's what happens with a diffuse reflection. You see, the rays of light that land on it in an orderly manner get scattered in all directions. And though we, an observer, might see light coming from that point, the image of the light source has been destroyed. And this is how we can see objects, and how sometimes we can see our reflection in objects.